Hi there, Mr. Boer here for the second video segment for week 3, and that's going to go over electron configurations. Last video segment, we talked about the Bohr model and how it is a good visual representation, but it only works for a lot of the smaller. As soon as you get too many protons and electrons, it doesn't work out as well. A better way to explain what the electron really looks like or what the atom really looks like now is using what electron configurations or the quantum mechanical model. Because basically, what Bohr, as he had suggested, that they are these orbits like planets that go around the sun, doesn't quite work for the actual model of the atom because we don't know how fast, we don't know the exact position of the electron. That's all part of the Heisenberg uncertainty principle, and you get to that in high school. But basically, it's a lot more complex than that. There are energy levels, as you had said. So you have something very similar how you have energy levels, but they're not all just going to exist in a certain area. What they eventually do is form these things called orbitals. And what an orbital is a probability of finding the electron. Basically, it's a mathematical equation at finding out exactly where the electrons exist. So they become these orbitals that we talk about. And get a little bit in depth that they're going to want to be closer to the nucleus because nucleus is positive and the electrons are negative. They're going to want to try and stick closer together. So the farther you get out away from them, the more energy that those electrons must have because they're being farther away. So we look at the orbitals that you have, but basically they are 4 different shaped orbitals: the S, P, D, and F, which then changes the number of electrons that you can have in each orbital. S can hold 2, the P can hold 6, the D can hold 10, and the F can hold 14 electrons. So as you go through this, it becomes something similar to what Bohr said, but slightly different. So as I said, the S can hold 2, the P can hold up to 6, which are going to be always given in pairs. So if we look at the S orbital, it's 1 pair. The p orbital has 3 pairs, the d orbital 5, and the f 7, which gives us those total number of electrons that we have. And again, the letters represent shapes. The first one's easy, basically. The S stands for sphere, and we can see here how they move in a spherical shape. It doesn't matter what part of your dimension you're on, the x, the y, or the axis. Doesn't matter how you represent that, it still looks the same. So if I was to say 1s, it's energy level 1, but a spherical shape. You would have one that's a 2s, so it's a larger, it's farther away from the nucleus, second energy level, but it's still a spherical shape. It's there that we start to get into some different shapes, which I call the dumbbell shape. But the dumbbell shape, as you see here with the p orbital, can exist on the x, the y, or the z-axis, and that's why there end up being 3 pairs of electrons. So the S can hold up to 2. Because there are 3 pairs, the P's can hold up to 6. Now, I won't get into the F or the D and the F. The D is basically what I always like to call a double dumbbell, and the F is a flower. It gets really, really complex. And where those shapes come from? Mathematical equations that give us the probability of finding it. The hard thing with using a quantum mechanical model or these electron configurations is to see how they all go together and why you can't just have a picture of it, because the 1s is inside of the 2s, which is all part of the 2p orbital. And you can imagine this is the simplified version of 1s, 2s, and 2p. Eventually, we're going to have 3s, a 4s, a 5s. We're going to have a 3p, a 4p, and a 5p, and eventually we add d's in there. So you can't really make a visual model. It becomes numbers and letters to represent the electrons. So what we look at here is if you have the different orbitals, again, the number that comes in front is going to be the energy level. The letter is going to be the shape. And if you notice, these boxes are going to represent at most 2 electrons in each orbital. And we said the P, because the X, the Y, and the Z ends up having 3 rooms. The D ends up having 5. If you multiply it by 2, that gives you your 10 total electrons. We didn't even show the F in here because we start getting into more complex ones. But that's going to have 7 rooms.